BCE 231. Okay, so last time, what I did is I just kind of gave you a quick look or a snapshot at what C programs look like. And what we're going to do is spend the next 4 lectures, so this week and next week, just running through the elements of C. And then after that, we'll move away from that and we'll start to look at embedded microcontrollers. So let's see, you should have my slides up on the screen. You'll notice that go ahead, Dave.
Your slides are not up on the screen. You've not shared screen.
Oh, I'm not sharing. Okay, that's what's wrong.
Now you're good.
Okay, so you'll notice I've got a big slide number up in the top right corner of the slides, 1 and then 2. And you probably saw the announcement that I suggested you bring your laptops to class. So this is the second time that I've taught a coding course. I taught this same course last year, and last year everybody was on Zoom. You know, we were all in a sort of a, you know, kind of a lockdown situation still, and we were all remote. And so this course was all done online. And since everyone was watching via Zoom, everyone's face was just, you know, a foot or 2 or arm's length away from their laptop. And so we had no problem with people being able to see the fonts on the code that I'm showing. And of course, there you are in the back of the room, and you're not going to be able to see the font on code if I show you a big piece of code. And if I try to blow it up so that you can see it, you'll be able to see the font, but then you can't really see the context of the program. So what I'm recommending that you do is bring your laptop to class. Download the PowerPoint slides, which are always posted well ahead of time before class. So you would download slide number 3, download lecture number 3 PowerPoints, get them running, and that way you can follow along. And when we get to something where we've got small font, you can see it right on your computer, and you'll know which slide I'm on because I've got the big slide number up in the top right. So we'll see how that works. Okay, just a couple things about giving you help. We did launch a Piazza site. I think most of you are probably familiar with it, but if not, it's a site where you can go and you can ask questions. You can pose questions. How do I do this? I'm finding, you know, when I try to download the Xcode developer tools, it's telling me I need tens of gigabytes. Whatever the problem is that you're having, you can pose a question either publicly, or you can pose it privately or anonymously on that site. And then the TAs, 2 of the TAs, will be monitoring that site, and they'll give you an answer to your question. They'll get it answered within 24 hours, but usually you'll get an answer much quicker than that. So the way you use one of these sites is if you've got a question, you just go to the site and you look around at the questions that have been posed and answered. And quite often, you'll find that the question that you have has already been posed and answered by the TAs on that site. And so it becomes a useful resource for you. So you have to just sign up for it. Simple enough to do. It doesn't cost you anything. Just so you'll know, the sort of the business and licensing model of Piazza is that there'll be a red box up at the top of the screen asking you if you want to voluntarily contribute some money. And if you contribute some money, then that red box will go away. And if you don't, that red box will stay there. It's sort of in lieu of an advertisement. So it's how they make money. But you can, the red box, it won't interfere with your learning. So it doesn't cost you anything then to use Piazza. You just go and you sign up. Okay. Now I also want you to know about the various kinds of office hours that we have available to you. So office hours, really it's lab hours and office hours. They take place either via Zoom or in the lab, which is Marston 221. And as I said before, that's a drop-in lab. It's a resource for you. You can go, you'll have these people there who can help you. Later on, once we get into some circuits and hardware and software, we'll have a spare parts depot there. Okay, just a little bit about what's on this slide. The areas that are shaded in cyan color, that's a light blue color, those are all the areas where the ECE department is not offering courses to sophomores. The majority of you here in the class are sophomores. So for the most part, those cyan colors are times when you all tend to be free from ECE classes. Now, you may have another class that's not an ECE designation, but this, for the most part, is when you are free. And so we put effort into making sure that we staffed the lab in a significant number of these time slots. Okay, you'll see the name of the TA that's there. So there's either one or two TAs. In some cases, in a given slot, let's look at over here at Ashton. Ashton Gray is, instead of being in the lab, he's there by Zoom. And you'll see the Zoom coordinates down in the lower corner. I see we don't have Ashton's coordinates there. We'll have to get that to you. Okay, what else do I need to know? You'll see I put some office hours for myself here, Zoom there Friday afternoon and also on Saturday afternoon. If it turns out that my office hours are creating a problem for you, you can't make them, then I'll add additional hours or change them. So my expectation is that between the help that we've got here with all of these people, either physically or via Zoom, or by using Piazza, that I think we have quite a few ways for you to get your questions answered. If you email me or text me, my first response is typically going to be, have you posted on Piazza or have you checked with the TAs? And why don't you go do that? I don't want to discourage anyone from contacting me, but just know that's, I mean, if you're asking me sort of a question having to do with the homework, quite often my first response will be, check Piazza or check with the TAs. But if you ever need me, you've got my number. I always want you to be, I don't want you to be reluctant or afraid to communicate with me via text if you ever need me. Okay. All right. What are we doing now? What we're doing is a crash course in C. I'm not trying to get you to be experts in C programming. This is not going to be as in-depth a course in programming like the way you learned Python last year, but it's enough to get you to be able to program these microcontrollers. We're starting out, we're doing everything on a computer with a console, meaning a keyboard and a monitor. And we're doing that while we're learning C. Then we'll move to the chips that don't have keyboards and monitors unless you specifically plug them in, but you don't usually have those things in an embedded application. Okay, just to give you a sense of where we are, I covered this last time, sort of the structure of a C program. What does it look like? I'd like you to all go out and run your own Hello World program, and that'll get all your tools up and working. And it's no small task to get everything working on your computer. You've got to get the editor working, you've got to get the compiler working and all that, and deal with the finite disk size that you have and all that. So it's can be a fair bit of work to get all that going. Okay, we're going to cover this stuff today, data and variable types. I'm going to throw a lot at you. I'm going to confuse you, and I'll tell you where I expect you to be confused, and I'll tell you not to worry about it because we'll work to unconfuse you as time goes on. Okay, and then on Monday on Monday and Wednesday of next week we'll cover the rest of this. Okay, this is just the slide that I ended with last time, and I just want you to, just in terms of what does a C program look like, the building block of a C program is a function, and all C programs have to have a main function. Okay, there are these things called preprocessor directives. We'll talk about them. You have to declare the names of things before you can use them. We'll talk about that today. There are 5 types of C statements. There are function calls, assignments, declarations, control, and then there's a null statement. Okay, and use comments when you code. The compiler doesn't care about them, but people do. Okay, and also when you choose names for functions and variables, you want to use good names for them, and we'll talk about what that means. Okay, so let's get into it. So C is actually a pretty compact language. There's not really a whole lot to the language itself. And here's a set of the key words in C. So these are These are particular words that the C language understands, and you're not allowed to use these for any other purpose. You're not allowed to use these as names of variables or functions, and if you do, you'll get a compiler error. And I put this up because what we're going to do is we're just going to go through, and I'm going to introduce a piece of it at a time, and as we do, we'll sort of check off the words on this list. And once we've kind of, we'll turn them red as we talk about them. And once we've done that, we will have finished our crash course on C. So I'll be coming back to this list. I want us to start out with this simple program right here. I called it age main 5. It's because it's a set of five programs. But what does the program do? Well, that's described in the block comment. It just prints a person's age in years. And it's part of a set of simple codes that I wrote to demonstrate console IO and variables, things called literals and constants. Okay. So now everything that's green is a comment. And so the compiler, that is the computer, ignores all of that. The rest of the instructions there are interpreted by the compiler. Okay, and so what we want to do is sort of study everything that's there. Okay, first we have this line, include stdio.h. Anything that begins with a pound sign, right? This is the pound sign or the hash mark. Anything that begins with that is called a preprocessor directive. It's not actually a C statement, but when we write code in C, what we want to do is get to a binary code that can be run on the microprocessor of your machine, right? And so in C, we compile code. We start out with source code, and then we compile it down to a binary executable, and then you run it, which is different from the way you did things in Python, where you'd have an interpreter that would interpret every single line as you went along. So here, the compiler is part of the game here. And these lines that begin with a pound sign, those are instructions to the compiler. And what this does is it goes to the C library and it gets a function, it gets a file called stdio.h, and it actually takes all the contents of that file and it copies them right into this before compiling. So it adds all the instructions from the header file stdio.h. It adds them to the code before compiling. You'll understand that more as we kind of get further into it. But for now, there's a function called printf, which stands for formatted print. There's also scanf, which is reading. We'll be using that to read input from the keyboard. If I go back to the previous slide where I listed all the keywords, I'll go back to that. You'll notice that there's no command for print. The actual C language itself doesn't actually have a command for printing to the screen. So instead, the C library, which is there's the language of C itself, and then there's an additional library that has all kinds of resources and facilities for IO and math and things like that. That library has a function called printf that allows you to print something to the screen or to a file or to somewhere else. And to make use of that, you have to use this command, the preprocessor directive, include stdio.h. That gives definition to printf. Okay, now let's look beyond that. Okay, we've got one function here. It's our main function. We're always going to define it this way: int main void. The purpose of those words will become clear later on. Functions always are surrounded by curly braces, an opening brace and a closed brace. Okay, so we have our main function here. Okay, now what's happening? It's just going to the program is just going to print you are blank years old. You are well. Let me run it. Let me go ahead and click next here, and this is what the output looks like on my. It would be, in this case, I'm running it on terminal, but if I were running it with command prompt, it would look very similar. What I've done first in this first line is I compiled the code. You only need to do that once, and then I run it. Every time I want to run it, I type /run Mac. Just sort of to review from Monday's exercise, when you compile, you specify the name of the output file from the compiler. So I compiled my source code. It was called age main5.c. That was my source code. GCC is the instruction to invoke the GNU C compiler. So it's going to compile that. And I told it I want my output file, the resulting file, to be called run Mac. So what that does, once you execute this, then you'll have a new file that will appear. It's called run Mac. It is a binary executable file. It won't make any sense to you, but it is understood by the microprocessor that is the brain of your computer. And so to run that in the Mac OS environment, you just type /run Mac. If you were running it on Windows, you would just type the name of it. And you can see this simple program just says you are 59 years old. All right, that's me. And then it stops. Okay. So if you look at the code itself, what I did is I defined a variable called age, and I set that equal to 59. And that variable is type int. It's an integer, right? An integer like 1, 2, 48, 59, as opposed to a floating point. It doesn't have a decimal point associated with it. So I just declare that integer, and then this line here just caused that line to get printed. You are 59 years old. At the end of our function, I have a return statement that just returns control back to the operating system in this case. So we've just dissected that program. And what I'm going to do is I'm going to show you a handful of programs, and we're going to dissect them like this. And what we want to do is be able to pull them apart and say, okay, what is every symbol? What is every word? What is every thing in here about? So let's go and look at, first, I want to tell you about identifiers. Okay, so identifiers are the names of the different things that you create and make use of in your program. So they're the names of objects such as functions or variables. Okay, so in this previous program, what are the different objects? Well, I had a variable that I used to store age, right? So I have one object is a variable called age. Printf is an object. It's a library function. And then main is the name of an object. It's our main program function, okay? And I want to show you more programs, and we're going to talk about the different identifiers, the names of things that we have in there. Here's another program. This program prints a person's age in years using a function called ShowAge. So this is going to do exactly what the previous program did. I've just changed the way I architected the program. So the previous program just said you are 59 years old. This one's going to do the same thing, right? Let me run it first. There it is. I compile it, run it. It says you are 59 years old. So it does the same thing, but I've architected this program differently. What I've done here is in the main function, I declare my variable age of type int. We'll talk about what that means. Then instead of printing it directly, I'm calling a function ShowAge, right? Show me the age, ShowAge. And what that does, that'll cause the execution to come down here, and it'll run this function down here. And I've just put that print statement down there, right? So now there will be no particular great reason to do this in a program, but I'm just doing this for you to see how I'm invoking a user-defined function, a function that I just created. I invented a function. It's called ShowAge, and that's where the printing out is taking place. So this program and the previous one do precisely the same thing. This one is just making use of a function. What I want to do is I want to talk about identifiers.
Professor, there's a question in the chat.
Oh, okay. Let me get the chat going here. Okay, can remote members turn their camera on?
Scroll to the bottom. That one's been answered.
Okay. Do user-defined functions need to be declared at the bottom of the file? That's a really good question. And we're going to get to that in more detail on Wednesday of next week. But in this particular case, the user-defined function is defined down at the bottom, right? So if you look at the bottom of the program, all of this down here, that's called the definition of the function. It has everything you need to know about the function, and it has the implementation, right? I've got the name, ShowAge. I specify that when you invoke this function, you're going to pass it a variable of type int, and it's got a name. And then we have the actual, we have the opening brace, the closing brace, the return. I have a complete definition of the function there. You could also put the definition of the function up at the top of the program. And why is it important? It's because what's going to happen is the compiler, it starts to, it'll start to process, and it gets, let's say it gets to this line right here. What that says is you're announcing to the compiler, I'm declaring, I'm going to have a variable here, type int, it's an integer, its name is age, and I'm going to give it the initial variable 59. From now on, the compiler knows what to do when it sees age. What about over here? It gets to show age, and the compiler says, what is show age? That's not one of my C keywords. That's not a library function. What is it? Well, what I've done is I've declared it up here, where I show void show age int semicolon, right? Why does it look like that? Why do I have int there? Why do I have void there? Why do I have a semicolon? This is simply the syntax of C at this point, all right? But what we've done is by declaring that's called a forward declaration. I put that up at the top of the file. That means when the compiler sees show age, it knows it's going to be a function. It's a function that we invoke by passing it an int, and it doesn't return any variables. So to get to Sebastian's question, if you want to define your function down at the bottom, then you have to put a function declaration up top. Alternatively, you can define that whole function up at the very top. Most references to coding style would recommend that you not do that. They recommend that you put your definitions of the functions down at the bottom of the file. That way, you can look at it and you can quickly look at your main function, and you could say, okay, I know what this thing is doing. I got the big picture of this program. I see my main function. I know what's going on. If I want to know the details, I can go down and look at those functions, and I don't have to hunt around to see main. So everything I just said there, we'll be talking about again a week from today. All right.
We have another question in the room here.
Okay.
So I want to ask, can you declare the function before the preprocessor directive?
Can you declare the function before the preprocessor directive?
You can declare the function before the preprocessor directive. Yes, you can declare it before the preprocessor directive, but you wouldn't want to define it before the preprocessor directive, and that's a bit of a subtlety. The difference between declare and define. The function itself, it needs to know what printf is. Printf, it gets that declaration from the preprocessor directive. You'll see that as we kind of get into this, sometimes it's necessary to put certain preprocessor directives ahead of others because there's a dependency there. In this particular case, you would not have a problem if you reverse the order of these two. Okay. Okay, why that the function has returned to 0 and the declaration of the function has just returned. Okay, so why? So if we look at int main void, what's going on there with the return? I mean, this gets a little ahead of when I plan to present this, but I'll go ahead and take up the question. So when you're running a program on, let's say, your Mac or your Windows or your Linux machine, you're invoking that program from the operating system. And so you have the option to pass values from the keyboard into the program if you wish. So you invoke the program from the operating system, and when the program is finished running, it returns control back to the operating system. And this business of void here, in this case, what we've done is we've specified an int. We specified a main program that does not take any input from the keyboard when you initiate it from the operating system. When we're finished, when the program's finished, it's passing back a value of 0 to the operating system using specified by this int here. That is important if you're writing applications that run on a machine with an operating system. Sometimes it's important for you to be able to know, did this program run correctly? And what often will happen is you might return one value back to the operating system if the function ran correctly, and you might return a different value back to the operating system if it didn't go correctly. So for example, return 1 or return 0. None of that applies when we get into embedded stuff because there is no operating system. It's what we call bare metal programming. So right now, what we're doing is we're writing code that you have to launch from your operating system, Windows OS or Mac. And this business of int main void and return 0 caters to that. When we're writing code for the microcontrollers, we'll still use this same syntax, int main void and return 1 and 0. It turns out you don't need to use the return because there is no operating system. It's one of those, I'll call it a quirky difference between running C on a console with an operating system versus on an embedded processor. I believe this will make more sense to you as we get into it in a week. Why does this other function that we created that I've already scribbled all over so you can barely see it, that one, it doesn't return anything. What we're doing is we're calling this function up top with the line ShowAge and then parenthesis age. I'm calling it, I'm giving it the value of the variable age, which is 59. But then when that program finishes, it's not returning anything back to the calling function. So that's why I have a void here. Let's leave that until we're going to hit that again in more detail a week from today. Okay, I want to show you more programs. So this is a different program, and the thing to keep in mind, what we're looking for here is just how are we structuring these programs, and then what are the different identifiers that we're using in the program, right? What are the whether the functions or the variables, what are the names of things in the program? So look at this next program. This program gets a user's birth year. It gets a user's birth year. That means we're going to get that from the keyboard. And it prints out age in years, days, and hours. All right, so that's what this program is going to do. It's going to ask the user, for the year they were born, and then it's going to compute what's their age in years, their age in days, their age in hours, and it'll print all that out. Okay, so let's quickly take a look at the code. Then I'll show you the output, and then we'll kind of dissect it. So we're making use of a number of variables here. We're going to have year of birth, right? We're going to ask the user to input that, and that happens right here. So here, these two statements, we're prompting the user, please enter the year that you were born. This line, scanf, will allow us to input from the keyboard the user input, and it's going to go into the variable year of birth. And in order for that to work, I had to have declared this variable year of birth. Okay, now down here, I'm doing some simple calculations. Age in years, right? Well, that's just, the current year is 2022 minus year of birth. So I had to declare that variable. I also have age in days and age in hours, okay? And what the computer is going to do is it's going to print on your next birthday, your age will be, And then it's just going to print out the values of age in years, age in days, and age in hours. So let me just run it for you. Okay, here it is. I run it twice. I've already compiled it. In this case, I decided to call it Let's Go 1. You can give it any name you want, but that's what I chose to call it. So it says, you know, I was prompted, please enter the year you were born. Okay, I was born forever ago. And it says on your next birthday, your age will be 60 years, 21,900 days, or 552,600 hours. Okay, then I ran it again. And I gave it, I said I was born in the year 2000, and it changed it accordingly. Okay, so we're not doing anything complicated here. But I just wanted you to see that compared to the previous programs, I have more variables and things that I have to give names to, right? And so when you're choosing the names for variables, and I'm going to say more about this in a minute, you want to sort of think through what you're calling them. And in some ways, the names of the variables I've chosen are kind of self-documenting. Year of birth, age in years, age in days, age in hours. Those variables make sense. You look at them, you sort of say, okay, I understand what's happening there. Okay, let me just tell you some sort of subtlety things here. Okay, look down here, age in years is 2022 minus year of birth. When I put 2022 in here, that is called a literal. We have variables. Age in years is a variable. The number 2022, right? Just like the numbers 365 and 24, we call those literals. Some people call them constants. You know, you have variables, right? A variable is going to be the name given to a slice of memory that you reserved for this thing called year of birth or age in years or age in days, right? The variables take up memory space. They're subject to change, right? Conversely, 2022 is not going to change. That's a constant. We call it a literal because constant means something slightly different in C, and I'll show you what that's about on the next slide. I just wanted you to note, I put the comment here that that's a hard-coded literal. All that means is I've got a number 2022, just like 365 and 24 down below. It's perfectly fine from the point of C to put these numbers down here, but sometimes you might look at it and you might say, why did I put the number 365? Why did I put the number 24? Suppose I have the number 6.02 times 10 to the 23rd or 212 or whatever number. You may not always know what the significance of a particular number is. I'm going to show you two other ways of coding these things that we call literals without hard coding them down in the code. Okay, so first, let me tell you a little bit about the law of C. Okay, so identifiers, these are the names of objects, of things like functions or variables. Okay, here are some requirements according to the C standard. You have to declare these identifiers before you can use them. So you have to declare, if you have a variable called int, a variable called x, I mean, and it's of type int, it's an integer. You have to declare int x before you can actually use it, before you can say x equals something. If you're going to have a function called myfunc, right? Before you can actually invoke that function, before you call it, you have to have declared it, right? So you have to declare things before they get used. What else? These names are case sensitive. So there's a difference between uppercase and lowercase. So if I write my age with a capital A or all capital, these are all different. So as far as the compiler is concerned, those are different variables. There are some style guidelines on when to use capital letters and when not to, and I'll tell you about those. Okay, when you're naming a variable or a function, the first character has to be either an underscore or a letter. You cannot use one of the C keywords as the name of a variable or function. The maximum number of characters that you can have in one of these identifiers is set by the compiler being used. So one of these C quirks we're going to find out a lot today is different compilers will tolerate different lengths of variable names, and different compilers will quite often do things differently. So you have to know what are the particulars about the compiler you're working with. Okay, just some things about good programming style. Use descriptive names. Don't begin an identifier with an underscore. Those are used for special identifiers. Just don't do it. If you're going to use a symbolic constant, I'll show you what that means. Reserve all capitals, all capital letters for symbolic constants. Not everyone would agree on this, but one style guideline is to use only lowercase unless you're dealing with things that are called symbolic constants. So my underscore age would be better than, they call this camel case because it has a hump in it, right? My age with a capital. Those are all just style things. So the first half of this are things that you gotta do according to C. The second half are things that are good to do from a style perspective. So let's take a look at some examples. Suppose that I have a variable and I want to call it my age. Well, here are a lot of ways of writing my age, right? And are any of these good identifiers, first of all? I mean, it could be my age. To write my age is a perfectly good sort of self-describing identifier. These are all different though, right? My age, all lowercase. I've got a capital E, capital Y. I mean, some of this gets a little silly, but these are all different, right? As far as C is concerned, they're all completely different variables. Just like if you look at XYZ, XY capital Z, capital X, capital Y, capital Z. Which of these are good identifiers? Which one should you use? Which one shouldn't you use? They're all valid. Let's talk a little bit about why you might use sort of, one naming convention over another. Okay, this is the same program that I just showed you, but I've changed the names of my variables. Whereas previously, let me go back. I'm gonna flip back to that previous code that I had scribbled all over. Right? We called the variables year of birth, age in years, age in days, and age in hours. They're relatively self-describing. Here, I'm calling them all age, but I'm using different mixtures of capital and lowercase. Yeah, and let's see. Yeah, I called this function age main bad. Let me just say a bit about the names that we give to the source program itself. And we'll say more about this later, but I'm telling you to create a folder, a project folder for each project you undertake and give that a name. So I think I called this project folder age. Often it's the case that you have multiple files, multiple source files that make up a project. You have to have a main function somewhere. So one convention is to always use the word main in the source code file that has the main function. If you only have I'll just leave it at that. I'll say more about that naming later on. But you'll see. When I give a name to a program, I'm usually taking the first part, which is the name of the project file, and then I'm calling it main because I have my main function defined here. And then if I have multiple versions of this that I'm using for demonstration, I might give them a number 1, 2, 3, 4, 5. More on that later on. But this one is. It does the same thing as that previous program, only look at what I've done here. I mean, it's silly, but for all those variables, I've decided to call them all age, and I'm just playing around with upper and lower case. It's perfectly valid, right? But it's hard to debug this. It's hard to make sense of this. I actually did this last semester. I did see a student who submitted some code like this. It was actually in a freshman course where we were doing some programming, and I actually saw something that looked just like this, where someone actually chose a word and used the same word for all the variables, but just made different upper and lower case. If if you do this, it's just much harder to make sense of the program. So this would not be an example of good programming style because everything is called age and it's hard to keep track of. I mean, if you get over here, if you're trying to debug something, you've got age, which is which. It's much harder to remember. Okay.
Professor, there's a question.
Okay.
So when we have declared the different ages, we have not initialized it with 0. So will there not be the garbage values in those variables? When you declare age, and age, they are not declared with the initial value. And I think the question is, what is the value it assumes?
Yeah, that's a good question. So in this case, we've declared them all. If we hadn't declared them, we would get a compiler error. They're not initialized in this case until I actually get to lines 18, 19, and 20, where I start to put some values in them. This one gets initialized here. So initializing is when it takes on its first value. In this declaration statement here, all you're doing is you're declaring them, but you're not initializing them. So they have no value yet. If you printed it out, you would get a garbage value. If you actually tried to print one of these out, but you hadn't initialized it, you hadn't given it a value yet, the compiler would give you a warning. It would tell you, hey, you're trying to compile some code here and you've declared this value, but you haven't initialized it. So be careful, right? And you don't want to ignore those compiler errors. You've probably done some MATLAB code by now. I've done a lot of MATLAB code. I think we often, or at least I often will ignore a lot of warnings that I get in MATLAB because I know I'm not going to go over a cliff with those. You don't want to ignore warnings in C, in the C compiler. More on that later on. But there's a difference when you compile between a warning. The compiler is saying, I'm just letting you know this, right? I'm going to go ahead and compile your code, but I want you to know there's a problem. And if you choose to ignore it, that's up to you. So in this case, to the question, the variables are all declared, but they're not initialized yet. In subsequent slides, I'll say more about initializing. Okay, so someone's asking, would age YR, AGE YR, and then age day and age month be acceptable names? Sure. I mean, I'm not going to be strict on what you call things. It's really mostly for you that you choose descriptive names. But I'm not going to. I'm going to be disinclined to say you can't use this or you can't use this. I mean, even if you submitted something that looked like this, it's not wrong technically, right? It's not good style. So you get a comment that says, from a style point of view, you'd be better off choosing different variables. But you have great flexibility in how you use variable names. Okay, what I want to do is show you some ways of dealing with these literals. So we have these hard-coded literals, these things down here that are sort of baked in down in the guts of the code. I want to show you some different ways of defining those. So in this next version of the code, what I've done is I've pulled out here, I've created 3 new preprocessor directives, and I've created what are called symbolic constants. And it's probably self-explanatory, but the first one, define current year 2022. That's a preprocessor directive. It says when you're getting ready to compile, every time below here you see current year, CURRENTYEAR, all capital. Every time you see that, just replace it with 2022. Likewise, every time we come across days in year, replace that with 365, and say likewise for hours and day. You can think about these as a macro substitution, if that language is helpful to you, or they're symbolic constants. All we're doing here is we're putting them up top rather than burying them down in the code. So now you can see where they're used, down here, and down here, okay? So how important is this? How useful is what we've done? Well,
Professor, we have a question.
Go ahead.
Is that the same thing as a global variable?
It's not the same thing as a global variable. here, this is not actually a variable, right? I'm glad you asked that question. So just a little bit about variables here in context of variables and scope. The question is, the issue of scope is, where is a variable visible? And often we're going to have programs that have multiple functions associated with them. For the most part, the variables that get initialized, that get declared and defined in a particular function are only visible within that function. They're not visible outside of the function. And this is done so that we can encapsulate the functionality of a particular function, write it in a function, get it working, and then not have to worry about it again. And it will only interact with the rest of the program through the header, the int main void, or the way we call it and the way it gives a response. And so C is designed in such a way that functions can be separate from each other, and variables that are defined within a function are only visible within those functions. That's called the scope of a variable. Sometimes, and this is particularly the case with embedded code, we want a variable to be visible, to be accessible to all the functions that we have. We call that a global variable, and we would define that outside of int main. Okay, in this case, we're not talking about variables here. Variables take up memory. All right, here we're just talking about some macro replacement symbolic constants. Notice that these begin with a pound sign, so these are preprocessor directives, right? When you compile, when you've got your code ready and you say, okay, I'm ready to compile this, the first thing that happens when you invoke GCC, and then output the name and then the name of the file, the first thing that happens is the preprocessor runs through and it does everything that begins with a pound. It goes and it brings library files in, and what in this case, the preprocessor would search through, and every time it sees an occurrence of current year, it replaces it with 2022. That's not a variable. There's no memory taken up by this. It's just a preprocessor action that takes place prior to the actual compilation. Why is it useful? Well, we just had a New Year's, right? So if I had written this code in December, I would have to go and change from 2021, down here, right? I'd have to change it in the previous code. I'd change it from 2021 to 2022. And you have to change it every year. It's easier to change something that's defined up here than it is to define something that's sort of tucked way down here, kind of in the bowels of the program. So there's a really good use case for something like the number 2022 being defined this way. Okay, what about 365 and 24? Those things aren't going to change. Well, I guess days and year could change on a leap year. That could change on a leap year, right? So maybe you'd want to keep it up there, to change it every 4th year. Hours in a day is not going to change. So that's not something that as a programmer, you'd be inclined to change. But I want to show you another way of defining these literals here. Oh, well, this was just me running it. That's not important. Okay, here is that same code, okay, but I've just written it. It accomplishes the same thing, but I've done it a little differently. I'm keeping this preprocessor directive here, all right, current year 2022, and then that actually impacts this line of code, okay. But what about those other two literals, those other two constants? Well, what I've done is I've declared as a variable that is a constant variable, meaning it's not going to change, right? It's a variable called days and year. It's a variable of type int. It will take up memory space, but I'm just saying this one, I'm specifying this as a constant. It's not going to change. And likewise, I have hours and day. I'm declaring that. That's going to be a variable of type int. We'll tell you about what that means, but I'm saying that's also a constant. Why do you do that? Oh, and by the way, those numbers get used down here and down here. What's the utility of that? You don't need to do it. You could just declare these as variables. But when you declare it as a constant variable, that just means you're telling the compiler, I've designed this program and I know that these numbers aren't going to change. If you see me inadvertently trying to change this later on in the code, give me an error when you compile. That's the purpose of this. So when you use constant, when you sort of modify a declaration with constant, you're just saying, as the designer of the code, I don't want to change this. If you compiler, as you're compiling this, if you see that I'm trying to change this, send a flare up, send a warning, because it's a constant. It's not supposed to change. So that's the purpose of this. It's one of those things that it's one of the many cases where the compiler can actually be your partner in building workable code. So that's what that's about. So I've just sort of shown you 3 different ways of dealing with the literals, the constants that we have here. Now, why am I calling them literals and not constants? Well, constant is used here, right? Constant actually means something here. That's why we don't call every single number in the program a constant. We call them a literal. Okay, so you can either hard code the literal. This is no longer hard coded here. You can either hard code it by putting the number down, down in the expression. You can use a preprocessor directed define statement that's called a symbolic constant, or you can use a constant variable declaration. All right. And I realize I'm throwing a lot of words at you, but when it's important, I'm going to be repeating this multiple times in multiple lectures to help clarify it. Okay. Before we leave this example code, let me just sort of show one more way of doing this. Here, it does the same thing, right? It'll accomplish the same thing. So from the user at the terminal, it's the same interaction as the previous one. Here, I've just written it, and what I've done here is I've taken, instead of creating new variables here where I'm calculating what is age in years, what is age in days, and age in hours, right? Instead of doing that, I'm actually doing those calculations right in the print statement, here, here, and here, and that's valid. So here, what I'm going to be doing is I'm asking the user to input the year they're born, and that's going into age. That's actually not a great name for that. It should have been called year of birth or something. But the year they were born goes in there, and then the actual computations of their age at their next birthday, the number of days that they've been alive, and the number of hours. Those calculations are all being done right in the print statement, and that's valid. I mean, there's not anything wrong with that. Another thing that's done here is you'll notice that I'm going to go back, I'm going to jump back a slide, right? When I get the input from the user, I prompt them with a print statement, please enter the year you were born. Then I have this thing called scanf, which reads input. Here, what I've done is I put them both on the same line, right? I've got the printf and I've got the scanf. Are you allowed to put multiple statements on the same line? The compiler doesn't care about white space. So the carriage returns, tabs, spaces, and all that, that's all for humans. So while the compiler doesn't mind if you put 2 things on the same line, it's not good coding style. It's not advised from any of the styling guides to do that. It just makes it harder to debug the program. And that's because our convention is that we put one instruction on a line. So if you were to show me this code or show it to one of the TAs or anyone and say, what's wrong with this code? We're trying to figure it out. Everyone would tend to ignore this because the expectation is there's only one instruction, one statement on a line. And if you put 2 on there, the compiler's not going to mind, right? But you might have difficulty when trying to debug it or if you're trying to share it with someone else because we tend not to do that. Okay.
Professor, we have a question in the front
I
row.
have a question. Yep.
Yeah, when you also do the %d sign, so what does it mean?
In the print statement, you have %d where you were putting in numbers. What does that mean? And why are we doing it?
That's called a format specifier, and we're going to get to that. So printf is not a C statement, right? Printf is a library function that comes in the standard C library, and the F stands for format. So it's a formatted print statement. And I've got some slides coming up in the deck that we won't get to today. And we'll dissect how that actually works. If you were writing a code that someone on a terminal was going to use, meaning a keyboard and a monitor, we would spend a heck of a lot of time on printf and a heck of a lot of time on scanf, and we're making use of standard input and output. Here, we're just going to cover this stuff a little because we're going to be designing apps that run on a microcontroller that does not have standard input and output. It doesn't have a keyboard, doesn't have a monitor, right? So we'll be kind of covering that, but sort of lightly, okay? Okay, this is that.
Question in the room.
Go ahead.
So if there are memory savings, why wouldn't you always use define as opposed to the constant variable?
Professor, the question is why would you use a constant integer if you're for it to save memory? Why would you use that instead of define and
Yeah, so the preprocessor directive doesn't use declaration, doesn't use memory. I mean, if you're really, we're going to cover next the issue of how much space things take. You know, if you have a handful of variables that you want to declare as constants, it's not going to take up a whole lot of memory. You could write them as preprocessor directives instead and save memory. It's really a question of how you want to build and document your code. In the previous program, if I were doing it, I would go with this structure here. The variable, or the literal that I want to change, would be this one here, current year. I would tend to put that there, and I would put the other two. I would declare them as constants here, and I would tend to do that because I'm going to show you later on an example of code that has a whole lot of stuff up here, right? And the more you have up here, the more things you have to keep track of. It sort of becomes a question of the style of the program. It's sort of like, the names of the variables that you use. How do you choose them? What style do you use? These become sort of style questions. But you're right. You could save memory by putting them up using preprocessor directives instead of consts. But I mean, certainly if you're coding to run on your laptop, for the you usually don't care about memory. I mean, you've got many gigabytes on your laptop. What we're going to find is the things that occupy memory are not the handful of consts. They're the arrays of floating point variables, things with decimal points. And I want to get to that next. Okay, so far we've just seen 3 of these variables, so I've highlighted them. All right, we saw int, which is one of our data types. Return is the end of a function. You can actually close a function without using return. They call it falling off the edge of the cliff, right? When you get to the closing brace, many compilers will accept the closing brace in no return statement. For our purposes, let's make sure that we keep the return statement. More on that later on. Okay, I briefly talked about what const was. So we've just so far just covered 3 of these words. I wanted to show you what happens if you go looking for trouble. Let's suppose that you deliberately use some of these words as names of identifiers in your program. Okay, so let's go and do that, right? So here's a program. I've called this bad var names, right? And it's written to demonstrate what happens when we attempt to illegally use a keyword. That's illegal, right? Or unadvisedly use a library function. So you're not allowed to use keywords for variable or function names. You shouldn't use your library function names, but you can get away with it in some cases. Okay. So here's the function we've created, right? So I've decided to be a knucklehead and create a variable, and I'm going to call that return. Now I know that that's that return is a keyword. So I know I'm going to get a compiler error, and we'll see that, right? Okay, then I have another variable x. In this case, I've done something what I haven't done previously. I'm declaring it and initializing it in the same line, and that's valid, right? Int x equal 100, right? So I guess we did see that with the consts in the previous one, but that's okay. Down here, I'm declaring a variable printf. I'm just asking for trouble by doing this, right? Because printf is the name of one of the library functions. And in fact, when the compiler sees this line up here, this include line, what it's going to do is it's going to go into the library and grab the file stdio.h, copy all the contents into the program, and that'll have a declaration for printf. That's going to create some problems. Okay, so let's go ahead and see what happens when I try to compile this. So the very first thing that happens is it throws a compiler error. It doesn't like int return, right? Right off the bat, we get a problem. And we were just sort of asking for it, right? So here what I've done is I've commented that out. When I put 2 forward slashes in front of a line, that turns it into a comment. So that's gone. So now what happens if I try to compile this? Well, this third line here, you know, we're looking for trouble with this, right? Because we're declaring a variable of type int, and we're calling it printf. We're giving it the same name as a function, and that function will have been declared in up here in stdio.h. So what happens when we try to compile that? It gives us an error, and it tells us something about int is not a function or a function pointer. It's confused, right? And here you're trying to figure out what's the problem, and the compiler is telling us, all right, the problem is down here, right? It doesn't know what to do with printf. Printf is, you know, this is a perfectly valid line of code, but what happens is this is occurring after I have redefined printf. Okay, you know, printf initially gets declared in stdio so that the compiler would know what it is. Then, being a troublemaker, I have I've declared a variable called printf, and so now it's confused. It no longer thinks about that as being a function. So I'm getting a compiler error, right? Okay, if I go ahead and comment that out, this will actually compile in this case. I've commented out stdio, which gave us access to printf, and I've commented out this, and I've commented out this. So I can, in this code, it will allow me to declare a variable called printf because I'm no longer using the function printf. Yeah, so I have a question in the chat asking, have we overridden the entire function printf? Yes, we've redeclared it, and so we've confused things. Okay, this compiles. That's the whole point. It doesn't do anything, but it compiles, right? I'm compiling it. I chose to use the output name bad, and when I run it, it doesn't do anything, but it compiled. Okay, so these are examples when we're doing things that, you know, we really should know better, right? If we try to use you know, one of the keywords, we'll get a compiler error and it won't let us compile. If we are trying to use some of the library functions, sometimes we'll get it to compile, but it'll behave badly, right? The thing to remember about C is C was written to always trust the programmer. If you insist on doing something, right, and you're not violating, you know, compiler rules, you may get warnings, and you know, the code may execute, but you could do all kinds of crazy things with the code, because C trusts the programmer, and it'll allow you to really screw up. But you need to have that if you're going to be going down and actually, you know, playing around with bits and memory locations right down in memory, which is what we need to do with microcontrollers. Okay. All right. Now let's sort of give a little more definition to data types. We've been using int. I've been throwing that at you, but let's sort of define this a little more formally. So data types in C, there are 2 kinds. There's numeric data types, and then there's character data types. And the numeric, meaning numbers, there are 2 basic types: integer, int, and floating point. All right. So the integers, the ints, they don't have a fractional part, right? It's just a number like 4, minus 36, minus 99, whatever. No fractional part. And most of the time, that's what we're going to be dealing with. But quite often, you know, we'll have analog to digital converters. We'll be measuring temperatures and things. We may have to be dealing with the decimal point. And so there's also a floating point kind of data type. So those are the 2 ways of representing numbers: the integer and the floating point. They're called int and float. We'll also have occasion to deal with characters. We'll be printing things on LED displays, and we'll be dealing a lot with characters. And so there's a char, C-H-A-R data type. Okay. In addition, we can create arrays of those things. You know about an array from your Python class. A set or a collection of things that have a common variable name. So we can have ints, we can have arrays of ints, we can have floats, arrays of floats, chars, and arrays of chars. An array of characters is called a string. Okay, this last point down here, I'm just restating that all of these things are called literals. So the number 4, minus 36, 98.6, A and Z in quotes, these are all called literals. Some people call them constants, but constant, as we saw, is used for something else. So we call those literals. And so what I want to do here is talk about how to represent literals and variables using these different data types. Here's an example, lots of examples, okay? Okay, what's this first line here? That's a preprocessor directive. We already saw that. I'm defining pi as 3.14. So this is a preprocessor directive. It's a macro replacement, a symbolic constant. And everywhere else you see pi, you'd know to substitute 3.14, okay? This line is just going to declare a couple of variables of type int, meaning they don't have a decimal point. They're just declaring them. I haven't given them any value yet. Float z, that's just declaring a variable z that's of type float. We care about the decimal point. This next line, int x equal 50, we're both declaring and initializing. I have a variable called x. It is of type int, and I'm initializing it to value 50. This whole business of int versus float is important because float takes up generally more space in memory than an int, because there's more to keep track of. You have to keep track of the base and the mantissa, right? You have to keep track of the decimal point, right? So these are just sort of more examples of the same. And I'm just showing you how we can do a combination of declare something and also initialize it, okay? Okay, now I'm going to confuse you, all right? I'm going to talk to you in some detail about the integer data type. So this is going to confuse you. I can almost guarantee it. So just let it wash over you. Hear it and let it wash over you, and we'll help to clarify it later on. So when we deal with ints, that is the integers, we don't have a decimal point. There are actually 4 different data types in C. They're called char, short, int, and long. So there are 4 different flavors of int. And generally, they have different widths. They take up different amounts of memory. And so therefore, they can handle different size integers. Okay, so that's the point here. They generally have different widths, and width refers to the number of bytes in memory. They can be unsigned or they can be signed. Okay, so signed meaning positive or negative, unsigned meaning it's just going to be positive. Okay, now here's the fun stuff. The rules apply. For a given C compiler, a short must not be longer than an int. An int must not be longer than a long int. A short int must be at least 16 bits. An int must be at least 16 bits. A long int must be at least 32 bits. And a long int must be at least 64 bits. Huh? Right? What this is saying is that a particular C compiler is free to interpret this any way it wants. You're going to provide 4 different integer data types: char, short, int, and long, right? Yes, you can have a long int, right? You can have a long unsigned int, right? And as long as C follows the specification, then the C language is proper, right? But what it means is you get hold of a particular compiler, and what's an int on one machine might be different from the representation of an int on another machine. And when I say different, I don't mean different values, but I mean the number of bytes of memory used to occupy it, and therefore the maximum possible number that you can store in it. So for example, if you have a short int, that means on many compilers, it'll only occupy 1 byte. That's 8 bits. As we'll see in a little bit, with 8 bits, you can represent numbers between minus 128 and plus 127, or between 0 and 255. You cannot represent the number 256 with 8 bits. 256 takes 9 bits. So 250, the number 256 would overflow if you tried to store that in a data type char. We'll look at this in more detail. So different compilers can interpret this spec differently, right? The C libraries also define what's called fixed width integers. That's going to be important, not now, but in a couple weeks. One more thing here, literals, these numbers that we're specifying, the number 255 or whatever, you can specify them in decimal, base 10. You can also specify that when you enter a number, it's going to be in hexadecimal. You put a 0x in front of it. You could be representing it in octal, or you can represent it in binary. And we'll spend most of our time when we're doing embedded stuff working between binary and hexadecimal. So I know this is going to confuse you. It's only going to get worse. Let me just give you some examples of some declarations and initializations. So I'm going to both declare and then initialize a value. Okay. So int x equal 100. That's fine. Okay. I could have signed int x equal minus 100. Okay. I've got the question, how does C know what base the literal is? If I just write a number 256, just like that, then it's going to be base 10. If I write 0x256, then you're specifying that you've entered a literal in hexadecimal. If you write 0, then you're specifying that it's an octal. If you preface the number with 0b, then you're entering a literal in binary. So by prepending X, O, or B, you're specifying that you're entering that literal in one of those different bases. Okay, and here all I'm doing is I'm just sort of showing you sort of a play on the literals 100 or minus 100. Okay, so minus 100 is a signed int; it has a negative sign. Here I could have an unsigned int of 100. I could have a short int minus 100, an unsigned short int of 100, a long of minus 100, and so forth. Right? What do you use when? Why? Why do we care about all this? Well, let's just say a little bit about bits, bytes, and nibbles, and then we're going to wrap it up for the day. So I need to get through a couple slides here. So if you go back to your logic design course, right, you remembered, you learned about flip-flops. And what a flip-flop can do is it can latch in a value of 1 or 0. It's high or low, right? How did you make a flip-flop? You know, you took some NAND gates and you cross-wired them so that they fed back into each other, right? And you might put some presets and clears on there, but you basically cross-coupled the output into the input of a pair of gates, and you had a flip-flop, and it could store a 1 or a 0 in there. And that's the basic element that we use in a computer for storing things. So a flip-flop is 1 bit, it's high or low, right? And computers are based out of, 100 gazillion of these kinds of things, okay? If you have 2 flip-flops together, right, there are 4 possible combinations. They can be both 0, they can be 0, 1, 1, 0, or 1, 1. If you have 4 bits altogether, you call that a nibble, by the way, there are 16 possible combinations that you can get. And I've listed them all here, right? They can be in binary, they can be all 0, right? And notice I put a B in front to represent that as being binary, or they can be, all 1s and everything in between, okay? So a nibble, a 4-bit nibble can represent 16 different things. We can also describe the value of a 4-bit value in decimal, right? And we know how to convert between binary and decimal, right? Let me just bring up this over here on the left, right? When you have this set of bits, right, you have on the right, you have the least significant bit, right? And then on the left, you have the most significant bit. And we know that there's a weight associated with each of these, right? Because they're in an order, right? So the least significant bit, it represents a value of 0 or 1. The next bit over, it represents a value of 0 or 2. The next one is 0 or 4, and the next one is 0 or 8, okay? And so in addition to going back over to the right side of the screen, in addition to talking about the value of that nibble in binary or in decimal. We can also describe its value in hexadecimal, right? Base 16, where you just use the digits 0 through 9 and then A, B, C, D, E, and F. Okay. Okay, so that's bits, bytes, and nibbles. The sort of the second to last slide here that I'll show you is, okay, suppose we take 2 nibbles, put them together, that's a byte, right? So that's going to be the basic building block memory element for our microcontroller, because that's an 8-bit machine. Your computer is a 64-bit machine, so it has 8 of these things strung together, your laptop. But our little microcontrollers has these as the basic building block. If you have 8 bits strung together, there are 2 to the 8th, or 256 different possibilities. So if you have a variable that occupies 1 byte, 2 nibbles, 8 bits, it can have 256 possible different values, okay? How do we allocate those values? Well, if we can agree that this is a positive number, right? If we say we're going to represent with 1 byte a positive number, then it can be anywhere between 0 and 255. You can't go above that, and we've agreed it's only a positive number. That's called unsigned binary representation. Well, what about negative numbers? Well, we can say, let's keep the uppermost bit for the signed bit, right? And if that is 1, we'll treat it as a negative number and 0 as a positive number. Well, if we do that, then we only have 7 bits for the magnitude. And in that case, we could represent numbers from -127 to +127. The limitation of that is you have 2 different values for 0, right? Because all the bits could be 0, or you could have 1 followed by 7 zeros. Is redundant, so you have 2 ways of getting 0. So close to what I've shown here, but a little different, is what's called the 2's complement representation. You've learned that before. It's kind of like reserving 1 bit for the signed bit. The point I want to make behind this whole thing is you can choose, if you have 1 bit, to represent a signed or an unsigned value. And you can specify this is going to be unsigned, meaning it's all positive, 0 to 255, or it's signed, and you go -128 to 127. Okay, we need to stop there because we're at the end of the hour. We're going to pick it up here next time. Things are going to get a little crazy and confusing, then they'll start to clarify. Okay, and I can stay here for a few minutes if you have any questions.
Like this particular slide, professor wanted to show which is behind it, or this thing came. So I